Find the highest order spectrum which may be seen with light of wavelength 4358 angstrom using a plane transmission grating with 5000 lines per centimeter. Here the data given is the wavelength of light lambda is 4358 angstrom, that is 4358 into 10 raised to minus 10 meter, and the number of lines n is given as 5000 lines per centimeter. That is, we are converting it into meter, that is 5000 into 10 square lines per meter. And we have studied the grating equation, that is the sine theta is equal to n lambda. This is the grating equation for normal incidence. Here theta is the angle of diffraction and capital N is the number of lines of the grating and small n is the order and lambda is the wavelength. Here the given, we are finding out the highest order spectrum. Therefore, in this equation, the order n is equal to sine theta divided by n lambda. That is, for the highest order spectrum, the n should be high. For n should be high, this numerator should be maximum. That is, sine theta should be maximum. The maximum value of sine theta is, this sine theta is equal to 1. Therefore, this can be written as n is equal to 1 by this n is 5000 into 10 square lines per meter into lambda 4358 into 10 raised to minus 10. That is, this will give the value of n as 4.5. That is, it will give approximately 4. That is, the first order spectrum is the fourth order spectrum corresponding to the wavelength 4358 angstrom and the number of lines 5000. The next problem is a parallel beam of monochromatic light is allowed to fall normally on a plane transmission grating having 6000 lines per centimeter, and the first order principal maximum is formed at an angle 15 degree. Calculate the wavelength of light. Here n, the number of lines, n is equal to 6000 lines per centimeter. That is 6000 into 10 square lines per meter. And the angle theta is given as 15 degree. And the quantity to be find out is the lambda. And we have the equation, grating equation, that is sine theta is equal to n lambda. Here the first order principal maximum. The first order principal maximum means n should be 1. Therefore, lambda is equal to sine theta by n. Substituting the values, we get sine 15 degree divided by n 6000 into 10 square into 1, and this will give a value of lambda as 4313 angstrom. And the next is a plane transmission grating has 6000 lines per centimeter. Find the angular separation of 504 nanometer and 501.6 nanometer of helium in the second order spectrum. And in the problem it is given that the n is equal to 6000 lines per centimeter. That is 6000 into 10 square lines per meter. And two different wavelengths are given. First we are taking it as lambda 1, corresponding to 504 nanometer, that is 504 into 10 raised to minus 9 meter. And for the second one it is lambda 2, it is 501.6 into 10 raised to minus 9. In the second order spectrum, that is n is equal to 2. That is the angular separation. We have to find out the angular separation of two different lambda, two different wavelength. And we have the equation, the general grating equation, sin theta is equal to n lambda. Here we have to find out the lambda. We have given two lambdas, and the corresponding to these two lambdas we have to find out the theta values. And for the first case we can write it as sin theta 1 is equal to n lambda 1. Therefore the theta 1 can be written as theta 1 is equal to, for this can be n and lambda 1 is, n is 6000 into 10 square into 2 into lambda 1 is 504 into 10 raised to minus 9. Therefore the theta 1 is given as 37 degree 17 minute. And for the second case, sin theta 2 is n lambda 2, and this will give 6000 into 10 square into 2 into the lambda 2 is 501.6 into 10 raised to minus 9. Therefore the corresponding theta 2 will be 37 degree. Therefore the angular separation of corresponding to two different wavelength, that is the angular separation is theta 1 minus theta 2. That is this 37 degree 17 minute minus 37 degree, that will give 17 minute. And the next problem is, in Fraunhofer diffraction, due to a narrow slit, a screen is placed 2 meter away from the lens to obtain the pattern. If the slit width is 0.2 millimeter and the first minimum lie 5 millimeter on either side of the central maximum, find the wavelength of light. So we have studied the Fraunhofer diffraction due to single slit, and the condition for minima as, that is the path difference delta is equal to a sin theta is equal to n lambda. This is the condition for minima. For n is equal to 1, we get the condition for first minima. First minima. That is, for the first minima, a sin theta is equal to lambda. And if the convex lens is placed very close to the slit, then the focal length of the lens is equal to the distance d between the slit and the screen. And if theta is very small, then we can write from the figure we have studied for a single slit, Fraunhofer diffraction at a single slit, theta is equal to, from here theta is small, theta can be written, theta is equal to lambda by a. And also from the condition x by d is equal to this sin theta or theta. So we have studied in the derivation of the Fraunhofer diffraction due to single slit. Therefore we can equate the two theta values. Then we get x by d is equal to lambda by a. That is, this x by d means when the convex lens is placed very close to the slit, then focal length of the lens is equal to the distance d between the slit and the screen, and we are considering the theta is very small. then we can write this theta is x by d. So where x is the distance from the first minimum from the central, that is from the point O, we have studied in the derivation. Therefore x by d is equal to lambda by a, and x means it's the distance from the point O is the central point. And therefore in this equation we can find out that as x is equal to d lambda by a, d lambda by a. Here in the data it is given that a screen is placed 2 meter away from the lens, that is capital D is given as. Capital D is 2 meter, and also the value of A, which is given as 0.2 into 10 raised to minus 3 meter. 0.2 millimeter, that is 0.2 into 10 raised to minus 3 meter. And the first minima lies 5 millimeter on either side of the central maximum, that is from the central maximum to the first minima distance is x. X is 5 millimeter, that is 5 into 10 raised to minus 3 meter. Therefore, we can substitute the values directly to this equation. We get lambda is equal to x by d into a, that is x is 5 into 10 raised to minus 3 divided by d is 2 into a is 0.2 into 10 raised to minus 3. And this we get finally a value of 5000 Armstrong, that is 5000 into 10 raised to minus 10 meter. And the next problem is a single slit Fraunhofer diffraction pattern is formed with white light. For what wavelength? The light in the second maximum in the diffraction pattern coincides with the third maximum in the pattern of 464.2 nanometer. That is, the light in the second maxima in the diffraction pattern coincides with the third maxima in the pattern for a wavelength. So, two different wavelengths and two different orders. And we have the condition for maxima in the case of a single slit diffraction pattern. We have already studied, that is the path difference a sin theta is an odd integral multiple of lambda, that is 2m plus 1 into lambda by 2, where m is the order, and here two different orders and two different wavelengths are given. So taking the first wavelength, that is the wavelength which should be find out as lambda 1, and the second wavelength as lambda 2, and lambda 2 is given, the lambda 2 is given as 464.2 into 10 raised to minus 9 meter, and lambda 1 should be find out, and n1 is given as, n1 is second maximum 2, and the n2 is 3, third maximum, that is the second maximum corresponding to a wavelength coincides with the third maximum corresponding to a different wavelength. That is, according to this equation, that is a sin theta is equal to 2m or n plus 1 into lambda by 2. 2 we can give it as n. We have, because we are represented two different n values. That is, for the first one, we can say the a sin theta is equal to 2n1 plus 1 into lambda 1 by 2. And for the second one, the path difference a sin theta is 2n2 plus 1 into lambda 2 by 2. So we can equate these two, that is 2n plus 1 into lambda 1 by 2 is equal to 2n2 plus 1 into lambda 2 by 2, and the by 2 can get cancels, and the remaining one is 2n1 plus 1 into lambda 1 is equal to 2n2 plus 1 into lambda 2. That is, n1 is 2. N1 is 2. That is 4. That is 4 lambda 1 plus lambda 1. That is 5 lambda 1 is equal to N2 is 3. That is 6 plus 1, 7. 7 lambda 2. 2 into is 3. 3 into 2, 6. 6 plus 1, 7 lambda by 2. Then substituting the values, that is 5 lambda 1 is equal to this 7 lambda 2. So lambda 2 is 7 into 464.2 into 10 raised to minus 9. And substituting these values, we get finally the lambda 1 is 649 nanometer. 649 nanometer.